Hello, my name is Artur Sinov. I'm from International College of Semiconductor Technology, National Chiao Tung University in Taiwan. Simulation of the nanoscale interconnects is a work where we build theoretical model for the electrical conductance of a defect in a nanowire using an extended approach of the point-like contact model. Outline of our presentation is simple. First slide describes a model, others describes a few applications. A defect, which we consider, is a geometrical constriction with a cylindrical symmetry located on a nanowire. The resistance of the defect usually gives a valuable contribution into the total resistance of the system. That is actual problem, especially for the nanoscale interconnects. To find this resistance, we calculate a charge current, which is a result of integration over the squared Bessel function with a few terms. These terms are responsible for the ballistic and diffusive electron transport. We also derive a conductance for the non-magnetic case in the symmetric point contacts. This approach assumes that the contact area can be replaced by the quantum object instead of mechanical defect because the applied quantum boundary condition contains quantum mechanical transmission coefficient. That makes the model to be easily adapted for the specific problem. The technical details are available in the published paper here. To prove a model, we made a fitting for the experimental data of the golden point-like nanocontacts. The blue curve is derived from equation for the symmetric non-magnetic case. This model describes diffusive, quasi-ballistic, and ballistic regimes of the conductance. Quasi-ballistic regime is somewhere here, since mean free path of the gold is around 38 nanometers. The complete model describes pin-resolved conductance for the magnetic systems as well. The rescaled previous figure with additional curve is shown here. This curve describes a conductance versus a diameter for the magnetic point contact. As a result, the total resistance of the nanowire is the summation of the resistance from homogeneous parts of the nanowire and resistance of point-like defect. The resistance of the defect is inverted conductance. Considering magnetic interconnects, such as cobalt nanowires, we simulated the possible magnetic configurations without and with presence of the domain wall. It allows to find the clear impact of the single domain wall resistance. The approach assumes that the electron spin is conserved along the transition of the domain wall area. Density of states on the Fermi level are inverted by value for the spin up and spin down electrons that induce domain wall resistance itself. Finally, a domain wall resistance is calculated by this equation, where the domain wall resistance from homogeneous parts becomes cancelled out, while the resistance of the defect is exchanged on the resistance from domain wall and without. So this is a result of domain wall resistance simulation in logarithmic scale in the case when domain wall width is a constant for simplicity. The resistance of the domain wall rapidly drops with diameter. A few experimental points were found from published experimental works. Finally, this is an example of another application where we exchange potential energy profile of the defect on the tunnel barrier and describe a contact between conductive AFM tip and the weak ferroelectric 2D material with presence of the screening effect and Schottky barrier. The current achieves the maximum and drops at voltage threshold, where the screening potential and Schottky barrier works against the tunnel transparency. The derived AV curves roughly reproduce this experimental data. So thank you for your attention.